Bats use echolocation, a sense foreign to humans, to navigate and find prey in complete darkness. Part of their biosonar system are morphological structures called noseleafs that surround the site of nasal emission. Noseleaf shapes are highly diverse across different species and are evolutionary adaptations to different biosonar problems. The anterior leaf, also called horseshoe plates because of their shape, the sella, and the spear-shaped leaf called the lancet. Recent experiments show that adaptation of bat biosonar systems are not limited to just static differences between species evolving over long periods of time. At least for some bat groups, like horseshoe bats, experimental evidence demonstrates noseleafs undergo displacements and non-rigid deformations. To simulate real-life dynamic motion of the lancet in digital models, we use animation techniques called skeletal animation, or rigging. The lancet is experimentally recorded to undergo about 12 degrees displacement across anterior and posterior direction. The acoustic far field for different positions and configurations of the lancet are then predicted numerically. Beam pattern maps are a function of frequency and azimuth and elevation directions. The colors correspond to normalized amplitude value. The dark red corresponds to highest amplitude of 1, while dark blue to lowest amplitude of 0. The effects of lancet rotation on the acoustic field are frequency dependent. At low frequencies of the spectrum, the beam width gets wider as the lancet rotates. At higher frequencies, however, the beam width remains largely the same, but the side lobes get stronger as the lancet rotates. Furthermore, as the lancet rotates, the main lobe direction shifts irrespective of frequency. In the end, we show that emitter dynamics have a strong effect on the acoustic field, but it still remains to be seen how these effects fit into the bat's overall strategy.